Hey everybody, my name is Eric Sammer. I'm the CEO at a company called Decodable, and today I'm going to be trying to lay out a blueprint for you to help you understand how you can build a real-time data platform that allows self-service to everybody within the organization, and I'm going to try and get it done in about under 30 minutes. The challenge is there's lots of really great open source projects out there, Apache Kafka, Apache Flink, Apache Pinot, so on and so forth. The real issue isn't so much do these systems work or do we know how to use them. The real issue is how do we stitch them together in a way that makes sense for everybody within the organization to be able to use. I'm going to show you what we've done at Decodable, and I'm not going to talk less about Decodable, the product and the company, and more about how we did what we did and hope that it helped you. So initially, I'm going to be talking about some concepts and building blocks that we used under the hood. The first thing that we always need to talk about is connectors. So connectors in Decodable, what we chose to do is place all of the connectivity to external systems, from getting data into or out of the internal platform. So that all that logic is contained within these connectors. They support both a source mode and a sync mode. They handle lots of system-specific concerns like authentication, authorization, serialization, deserialization, including things like the protocol, like how do you talk to these systems, so on and so forth. In Decodable, we actually separated the streams that come out of these connectors or go into these connectors into what we call append streams and change streams. Some of them even support both modes. I'm going to talk more about this in a little bit. These connectors can either operate in real-time mode or batch mode. And in real-time mode, they feed event data out if they're a source, or they consume data in real time as a sync. But also some connectors can actually operate in batch mode where they wake up every 5 minutes or so. They'll consume a bunch of data, bring it into the system, or if they're on the sync side, do the opposite, the other direction. Some connectors operate in parallel mode, whereas some are effectively singly threaded. Think like change data capture coming off of Postgres databases or MySQL, those kinds of things. Whereas some may really scale out where you're connecting to large parallel systems like Apache Pinot or Kafka, things like that. We call configured instances of these connectors connections. And so connections always have a connector type. You might have a Postgres connection or a Kafka connection. The connection itself is always either a source or a sync. And again, sources are reading from external systems and they write to a stream inside of the platform. And on the output side, the sync side, they read from a stream and they write to that external system. Connections are sort of like Kubernetes services in that they have a target state, which is the state you want it to be in, and then an actual state, which is the state that it's currently in as it tries to work its way toward the target state. So if you say, I want this to be running and it's currently stopped, you get the idea. It sort of goes through the motions and works its way towards a running state. There's always tons and tons of connection-specific properties. They will depend on the particular piece of technology, again, Kafka topic, or parallelism factor, or the number of partitions, those kinds of things. Streams are really similar to a Kafka topic or a Pulsar topic or a Kinesis stream. They have all the same properties as those, but with additional semantics on top of that. And the reason why we've done this is because we found that the current definition of a topic kind of leaves a little too much flexibility for most people in most use cases. Streams can now, of course, have many producers and many consumers, just like a Kafka topic, but they always have a schema attached to them. And I'll get more into schemas in a little bit later. These streams are either append mode or change stream, but they're never both at the same time. So they are either always in append mode or always in a change stream mode. And they have a bunch of optional parameters like primary keys that decide or can affect different partitioning schemes. They have indication of which field carries the semantic event time within each record, watermarking strategies, all sorts of other things. Again, we're a stream processing platform, so we care very much about these kinds of things. So change streams are effectively encode insert operations, updates, deletes, the operations to a particular record. And that record is indicated by a primary key, just as it would be in a typical operational relational database. Change streams always include both a before version of the record and an after version. So in the case of like an insert, there's no before, there's only an after. In the case of an update, you have the previous version of the record, and then you have the new version with the result of the update. Internally, we always use the Debezium format or envelope format for representing these change streams. And I've included here on the slide an example of what one of these looks like. So the key here contains what the user may have indicated as the primary key, in this case, a user ID, lucky number 13. The value is the Debezium envelope format that I talked about. So it's got an operation. Here it's a U because it's an update, but it could be like an insert or delete. And then you have the before version where the user status was active, and then it transitioned to an inactive state. Append streams, on the other hand, are like a change stream conceptually, but they only represent insert operations. So basically, it's an optimized format of the record. And that's because we don't need to encode things like operation and all these other kinds of details because it's implicit in the format. So we don't have, and we don't include the Debezium envelope format because it allows us to save a bunch of bytes on the wire and get a better efficiency of not just storage and transport, but processing of that data as well. So here's like a similar record, but in this case, an insert only, where we might have a bunch of different fields, but we're just showing this one status field. You get the idea. The schemas that I keep referring to, I just want to kind of call out, we always use the SQL type system for schemas. And the short answer to why that is because everyone knows it. And as much as possible, we try not to translate between different type systems where, maybe some support signed types and, not support unsigned types, those kinds of things. We really want to remove as much of that. It's flexibility, but it's flexibility with no like real value for the people that we want to be able to use this kind of platform in anger. So in addition to just supporting the types, we also support constraints. And so this is where people can encode business checks like, not null enforcement or check constraints, like to check the length or the particular format of a value. And we support the ability to map into the user record space what we call metadata fields. Some people call them virtual or computed fields. Metadata fields tend to be technology specific, like in the case of Kafka, like on the Kafka connector, for instance, that metadata includes things like the topic name or the partition ID, the offset within that partition. For things like Postgres transactions, coming from a CDC stream from a Postgres source, those could include things like transaction IDs and source table and all sorts of other metadata. Pipelines are what we call a job, and it's really the unit of processing. So this is kind of like the bread and butter, the meat and potatoes, if you will. In our instance, we represent all processing as SQL, and I'll talk a little bit more about why that is. But these SQL statements are always in the form of insert into my output streams, select from my source streams, and of course we support things like joins and aggregations and all these other kinds of things. There's pipelines, it's important to point out, they always operate on the streams. And the reason why is because it removes the complexity of the connection information, which typically, at larger organizations at least, different teams have responsibility for. So if you're the Kafka team, you can expose a bunch of streams that other people can use in their processing pipelines. They don't actually have to know which broker cluster it comes from. They don't have to know all of the details around the deployment. So they can focus strictly on the business logic and the schema that they're receiving as input or output. We use Apache Flink under the hood. So the Decodable stream processing platform is powered by Apache Flink. We chose this because it is incredibly powerful. It's open source. It's Apache licensed, which we like. And it really is proven at scale by some of the largest deployments. If you do a little bit of Googling, you can find out who some of those people are. I don't want to name any names. And in that, it supports stateful stream processing. So there's some myths about stream processing that it can only process one record at a time and things like that. In fact, modern stream processing systems, including Apache Flink, and as a result, Decodable, support not just current record by record processing, of course, that's common, but also stateful operations like complex event processing use cases, like this event followed by that event within a 5-minute window, aggregation operations, and including complex joins. Queries themselves can output either append streams or change streams based on the query operators. So for instance, if you have a pipeline that is simply doing some windowed aggregation, maybe it only ever outputs new data. But there are cases in Flink and Decodable where you can actually group by, for instance, and aggregate on non-time-based fields like user ID and count all of the events that a user generated. And in that instance, you may have to issue updates to that count. And so it's really, really important to be able to support both kinds of operations. I won't get into a ton of detail. I'll just say that, like, of course, this has to have a rich function library for being able to do all the common sort of streaming ETL, data formatting, aggregation, real-time analytics kind of use cases. So everything that you would normally find in a typical SQL-based system, we support, and Apache Flink supports as well, and you should too. The system catalog is where sort of things start to get a little bit interesting. The system catalog is sort of a generic term that we use for all of the definitions of objects and the management of those, what we call resources. So organizations and accounts, like your company name, and then all the different teams or business units within the company, users, groups, roles, things like that. And then sort of, again, the bread and butter resources, which are namespaces, connections, the streams, and the pipelines that I described earlier. In addition to just managing those resources, the catalog provides a bunch of discovery and analysis tools, like which of these resources are currently in use, understanding dependencies and lineage information, understanding schema compatibility. Can I use this stream with this particular connection, as a for instance? Complexity, and then of course performance analysis and complexity kind of go hand together. This is just how many resources does this pipeline actually need based on the computational complexity of the pipeline and what it's doing. The performance being things like speeds and feeds, how many records in, how many records out, bytes in, bytes out, those kinds of things. And of course, the status, is my pipeline currently running, which, let's face it, is sometimes a harder to answer question than it should be. Okay, so those are a bunch of the building blocks. I want to get into a little bit about the architecture and sort of how we stitch these things together in order to form this platform that we can give to people. So we separate everything into a control plane and a data plane. The control plane provides access to and management and analysis of all those kinds of functions. Some of the components and functions in that are the UI and the API access, and then sort of a bunch of what we call subservices within that: account management, identity, authentication, authorization, or IDP support. The system catalog that I just described, job control, the start, stop commands, get status, those kinds of things. And then the ability to query and analyze what we call system events and metric events, or metrics that are happening within the product. And so this is kind of what the control plane looks like. You can see that there's a UI, there's the command line interface, a bunch of SDKs that are built on top of a standard API, which we also allow people to access directly if they need to script things through CI/CD processes and those kinds of things. And then under it live all of those functions or components that I described earlier. Pretty straightforward, but it's worth thinking about these things as sort of an isolated part of the architecture. The data plane is kind of, if the control plane is all about command and control, the data plane is the hot path. That is where we actually connect to data. That is where we manage the streams, and that is where we actually do the stream processing infrastructure, or the stream processing work. The data plane actually receives commands from and reports status back to the control plane. So there's some complexity in sort of how RPC calls are made and those kinds of things. I'll sort of set that aside for a sec. And I'll just say that there's bidirectional communication between those two pieces of the system. And this is where the pipelines run. This is where pipeline state storage lives. The streams, which again, you can think of it like sort of like Kafka topics or Pulsar topics. This is where low-level job control actually functions about reconciling jobs to their desired state. And this is where the actual event storage and metric information actually lives in the platform. So the control plane simply queries this data. The goal is to have all of the sensitive data separated out from the control plane. There's a different set of security constraints around the data plane versus the control plane. So this is kind of, the data plane is a little bit more sophisticated, but this is kind of logically what it looks like. You have all the different functions, and then you have many, many, many connections, streams, and pipelines that form these end-to-end data flows that are running in production. In terms of practical use, like all of this stuff is probably, maybe you've heard this stuff before. I want to talk a little bit about how we see people using this successfully, because there's lots of different ways you can use it. Not all of them are successful. So I think the first thing that's important to talk about here is ownership and the notion of self-service. The thing I'll say is whenever I talk to people trying to build these kinds of systems or run these kinds of systems is that everything, absolutely everything, every connection, every stream, every pipeline, every account, every user has to have an owner. It can be an individual in a small company, or it could be a team in a larger organization. And what we have found is that you should think about streams as the API to serve or vend data, kind of hand data off between different parts of your organization, different lines of business, maybe even different microservices, those kinds of things. And then encapsulate the private resources, the connections that maybe nobody has business messing around with other than your team, if you're on the serving side, or the target connections, if you're the analytic data or customer-facing user analytics team, maybe you're running Apache Pinot, you're going to be the best position to configure that connection and do the processing and get data into that system. You don't care so much about where it comes from. I would say, in general, the standard microservice rules apply for sharing. Owners of a service, in this case a stream, provide a public API. And they maintain the contract on that public API. They might do a bunch of stuff behind the scenes in order to support it, but that is the interface by which other people can consume that service. Clients, of course, can do whatever they want with it and bank on the contract remaining reasonably stable. And I'm going to talk a little bit about schema migration in a second. So here's some of the common ways we see people using it. So for instance, if you just need to serve a simple stream, no transformation, and you kind of want to abstract the configuration for security reasons of like where this data comes from, because maybe nobody has business accessing a particular Kafka topic or Pulsar topic or something, or operational database, you might choose to create a private connection and then create a public stream that then other teams can build pipelines and sync connections off of. Okay, really simple. Slightly more complicated is maybe you need to maintain backward compatibility. You need to clean up that data in some way. You can add a pipeline to process the stream, and I've omitted the source connection here just for brevity, and be able to still maintain that public stream that, again, other people within the organization can use, but they don't care. They don't know that additional processing is happening behind the scenes. And again, it's just like a microservice. We're not firing rockets into space. This is pretty straightforward stuff. It's worth pointing out that nothing precludes you from both serving the stream and using it for internal private use cases. So if you're the team that is responsible for getting all the clickstream to a retail site, you might also build downstream pipelines yourself, but you can also serve that clickstream data to many other teams within the organization. You just have to decide what is the public resource that is facing the other teams. And of course, nothing stops downstream teams from building further public APIs on top of your public API. Again, just like microservices, you can put a service in front of them that also has a public API. It's worth pointing out that anything that anybody builds on has to have, can have a lesser contract. It can be development supported on a production-based API, but not the other way around. I haven't mentioned user-defined code yet, and there's a reason for this. The way that we encourage people to interact with the system when they have to drop down into low-level Java or Go or Scala or Python, whatever your weapon of choice is to really think about this as external functions outside of the engine. And it's not that systems like Flink or Decodable couldn't support these kinds of things. In fact, some cloud providers and vendors do. The thing that we have seen in production is that code being opaque to the engine means that we can't optimize optimize it the same way. There are security and isolation concerns. And quite frankly, it causes quite a bit of stability challenges around things like memory consumption and all these other kinds of things, because the planner of the engine can't know by definition what's happening inside of that code. And so what we tend to do is loop that external function in by using by having a system like Decodable produce data to a Kafka topic or Pulsar, again, whatever your Red Panda, whatever your weapon of choice is, process, and then loop back in. So you're basically, we call this like an external function. And we have found that this is not only safer for the platform, and as a result, all of the production infrastructure that lives on top of these pipelines, but it's actually easier because the people building that function, or at that point, it kind of becomes like a microservice. The people building that actually don't have to be constrained by the way the framework works. They can use their own methods of CI/CD and deployment, and they can have their own dependency chains, all sorts of stuff like that. So I would strongly encourage you to think about using this as a cut point between the inside of these kinds of systems and the outside. In terms of schema migrations, and I had sort of glazed over, this is a really sort of hot button item. In general, even if you don't use SQL, with something like Decodable, I strongly encourage you to follow SQL style migration rules. Schemas can be evolved in sort of well-known ways that your users understand, and this promotes that self-service that we're going for. Resources are either in production mode or development mode. I'll talk more about that just in a sec, very briefly. And these modes wind up enforcing a bunch of rules that the system can use to understand what's permissible and what's not. So in production mode, backward compatible changes are allowed to happen in place. So you can add a non-nullable field or a field with the default to a stream, for instance, but backward incompatible changes effectively create a new version of an output stream. And the reason why we do that is that stops us from breaking all of the downstream services and teams that are dependent on our resources. Prod resources, of course, can only depend on other prod resources, right? They require everything upstream of them to be able to support that level of contract. And the important thing here is that nothing will break if you follow those rules. Although data can stop flowing, but you'll never actually blow up a downstream service. In development mode, this is sort of what we call clown mode. This is where you can do whatever you want, like, it's like YOLO mode. In this case, you can do backward incompatible changes in place. It's when you want to iterate very, very quickly. It winds up being helpful for a short period of time, and then you transition into a production mode. Dev resources can depend on either dev resources or production resources. And just know that when you're in dev mode, things may break. And that's it. With this kind of blueprint, you'll actually be able to connect to any source, any destination, transform, enrich, join, whatever your favorite verb is, in whatever language your users already know. We chose SQL. We think it makes sense. You can do something different. You can also send to a couple of really interesting places. So real-time and offline analytic systems, and this includes things like Apache Pinot, which we're very excited about, but also more traditional offline database systems. Operational databases and caches, so you can do change data capture out of them. You can also insert records back into things like Postgres and MySQL, or even caches like Redis. You can build event-driven microservices off of the same infrastructure. You can ingest data from or send it to SaaS business applications like Salesforce and other things like that. And of course, drive ML and AI pipelines for sort of the mathletes in the crowd who want to be able to do online inferencing and model serving. I want to thank you so much for hanging out with me. Hopefully this is useful to you. Thanks to the StarTree team for putting on such a great event. And if you want to give it a shot or you want to reach out to me, feel free. Thanks so much for your time. Take care.